Hi everyone and welcome back. In this video we're going to look at when z-scores are not exactly 1, 2, and 3 standard deviations away from the mean. So if you'll recall, we looked at a problem in the last video about cereal. Please feel free to pause the video and reread the problem so that you have an understanding of what the background is. What we're going to do right now is take the problem that we just looked at and change the scenario a little bit. So the company's lawyers say that 6.7%, which is what we found in the problem earlier, is unacceptably high. They insist that no more than 4% of the box can be underweight. So the company needs to set the machine to put a little more cereal in each box. What mean setting does it need? Okay, so since I'm given a percentage, remember, that means I need to use inverse norm. And the area would be 0.04, my mean is 0, my standard deviation is 1. So what I need to do is go to my graphing calculator, and I'm going to do inverse norm. So we access at the same place we get normal CDF. You go to second vars, and this time we're going to pick number 3. And again, my area is 0.04. Remember to put your comma, 0, comma, 1, and then enter. And you get negative 1.75. So remember, that's your z-score, which makes sense because we know that 6.7% would have been a higher z-score, and we had got negative 1.5 for the flag for that one. So now, with that information, remember what I'm looking for here is what the mean setting does it need to be. So I'm looking for the mean. I have the z-score. I also have the weight of the cereal boxes, and I also know the standard deviation. So I'm going to plug that into my formula. I know z equals the weight of the boxes, which we know is 16 ounces, minus the mean. So I'm looking for the mean, which is mu, and my standard deviation is 0.2. And I need to solve for mu. So to do that, I'm going to multiply both sides by 0.2. And when I multiply 0.2 times negative 1.75, I get negative 0.35 equals 16 minus mu. And then I want to solve for mu, so I'm going to subtract 16, and I get negative 16.35 equals negative mu, and of course you can't have negative mu, so we're going to multiply by negative 1 to get positive mu. So that would just be 16.35 equals mu. So what does that mean? It means that the company must set the machine to average 16.35 ounces of cereal per box. Okay, using that same problem, same values, the company's president vetoes that plan, saying the company should give away less free cereal, not more. Her goal is to set the machine no higher than 16.2 ounces and still have only 4% underweight boxes. The only way to accomplish this is to reduce the standard deviation. What standard deviation must the company achieve, and what does that mean about the machine? Okay. So using the same information I had before, I want to figure out like where my value of 16.2 stands. So I've got my formula, which is z equals y minus mu over sigma. And by the way, sometimes I might, instead of using y, I might use x. It's just a variable. So I know that my z-score was negative 1.75 from the last problem, okay? And I know that y is 16, And my mean I just found from the last problem is 16.2. And I'm looking for the standard deviation, so sigma. So how am I going to solve this? I'm going to multiply both sides by sigma. And they cancel there. And we get negative 1.75 sigma equals 16 minus 16.2. And I know that I can combine 16 minus 16.2, you get negative 0.2. And then we're going to divide both sides by negative 1.75. And we would get sigma equals 0.1143. So remember, we were looking for what the standard deviation must be, which is this. And then what does this mean about the machine? So it means that the machine must be more consistent in filling the boxes, right? Because our original standard deviation was 0.2. So that means that our standard deviation decreased, which means there's less variation and more consistency. So we can just say that this means the machine must be more consistent in filling the boxes. Sometimes it's safe to assume that the underlying data distribution is roughly unimodal and symmetric, but not always. Regardless, you must always remember to check whether a normal model is reasonable, because if it's not, then the percentages and answers you found don't make any sense, right? So what we can do to check for normality is to sketch a histogram or a dot plot. But another way, and I actually prefer this way, is to create something called a normal probability plot. What the normal probability plot shows us is if the distribution of data is roughly normal, then what you'll see on the plot is a diagonal line, diagonal straight line. Okay, so here's a histogram and its corresponding normal probability plot for that gas mileage data we looked at for the Nissan Maxima in chapter 4. You can see by looking at the histogram, it's approximately unimodal and symmetric, so the normal model would be applied. And if you take a look at the normal probability plot, you can also see it's roughly a straight diagonal line. There's a couple stragglers which could represent your outliers or potential outliers, but overall it's a diagonal straight line. So that means it's safe to apply the normal model. Okay, let's actually make one. So we're going to take the drop heights that we looked at in feet for the 12 steel track roller coasters, and we're going to create a normal probability plot for that. So to do that, what we're going to do is go into our calculator. Since we're entering data, remember we want to go to stat and then enter. And remember, if you have anything in your list, you can clear them by just scrolling up to L1 and click on clear and then hit the down arrow, and you should see those numbers disappear. And that goes the same for any of the L's, the lists. All right, so I'm just going to type in my data values. And once I have those entered in order to make a normal probability plot, we're just going to go to second y equals, and we're going to make sure our plot is turned on. And we also want to scroll down to where it says type, and we're going to click on the very last graph we see. That's the normal probability plot. Hit enter. Just make sure your data list is an L1. And we can leave it the data access X. And then remember, you're going to hit zoom 9. okay? And as you can see there, you can see that it's roughly linear. There's a couple data points like around that one between negative 0.5 and 50. You can see that or negative 0.5 and 0, you can see that they straggle a little bit from the line, but overall it's a fairly straight line, and it's okay to use the normal model to make some estimations. Now, that little straggly part there could mean that your estimations might be off a little bit. But again, we're dealing with real life data and it's never going to be exactly perfect. So, it is okay to have that little deviation there. And overall, it's consistent with the line. So it would be okay to use the normal model. And that's it for this video. If you have any questions, please reach out to me. I'm happy to help, and have a great day, everyone.